Okay, so now we're recording. Welcome everybody to lecture six. This is the last lecture that's more generic. Basically, as we're kind of reaching half point, we are going into multimedia data, basically either at the end of this lecture or really at the beginning of the next lecture. And sort of transition our way from this sort of engineering framework that we built up into what does this mean for multimedia, how do we connect the two, and then obviously from there on into, and this is all the things we can do with multimedia and how to understand this kind of stuff. And of course, then everything becomes a lot more practical, a lot less sort of mathematical exercises, a lot more, you know, real, actually interesting stuff. Yeah, let's just go for it. We will talk a little bit about generalization today, and we actually didn't finish last lecture slides, so I'm going to actually bring in the slides a little bit first. But then the idea was to do generalization, and then also talk about a desirable examples, sort of in a quick way. And then we'll actually start to ask ourselves, okay, as we now go to multimedia data, the trick is that we don't actually work with sort of, you know, binary functions or structured data anymore. We work with data that directly comes from some sensors that are basically a mirror of the universe, right? And so what happens there is that we need to be dealing with noise and other phenomena that we have when we use sensors, and a very, very good discipline that knows how to deal with that is called physics, but also information theory. So I will keep it always to information as much as I can, because I don't want to like ask you to have a physics background, but I will show you some of the physics that's related to it, so you see where that information stuff actually comes from. Then, you know, we will really easily understand why we need convolution layer, what they actually do, and you know, how we figure out how many we need, and all of these kind of things. So the actual sort of deep learning quintessential stuff. Okay. First of all, however, we agreed that there were questions for the homework after I released the homework. So I released the homework yesterday. Do people have time to look at this, or should we wait a couple more days? Should we do it in office hours? How do people feel about it? Should we go through the homework now? Indifferent? Oh, sorry, that was a different presentation. Give me a sec. So we need Dropbox. Let's go to the homework now. It's quick. So, and then we go to here we go, fall 2020, homework 2. Oh, right, homework 2 solutions. Here we go. Okay, so this was homework 2. Homework 3, by the way, is up now. And again, it's, okay, people want me to go through the homework. Perfect. Homework 2 and homework 3 is up right now. And this is homework 2, okay? For some reason, I lost the pages file, so I need to go through a PDF from last semester, but this shouldn't do anything. So how many states can n Boolean variables assume? Well, each variable has 2 states. And so that means you have to multiply 2 by 2 by 2 by 2 by 2 n times. And guess what? It's 2 to the power of n, okay? So this is kind of basic stuff. How many functions can be built from n Boolean variables to a binary label? That's also the interesting one, because now we got to ask ourselves, okay, we have 2 to the n states, but we can then map that to a different sort of function each, and it becomes 2 to the power of 2 to the power of n. We discussed it in lecture earlier, but I was just gonna basically repeat that. And now we get to a little more interesting. How many functions can be built from n Boolean variables to a k class labeling? Right, so each of the 2 to the n states can then be mapped to k states, right? It's not 2 anymore. So then all you have to do is not go 2 to the power of 2 of n, but k to the power of 2 of n, right? And you see how big these numbers go so quickly, right? And now you assume an arbitrary table with m columns and n rows. How many different binary labelings can be created for that table? Well, the funny one here is that n rows imply simply 2 to the power of n binary labelings independent of the dimensionality of the row, okay? So you could have a 20,000 attribute table. If it's just a binary labeling, it's 2 to the power of n, done. And that's very interesting because that has implications, and that also explains why, a little bit why the McKay curve follows this, because basically as your attribute count goes to infinity, right, but you still only have binary labeling, then of course it's easier and easier to compress, so that curve that basically goes up, okay? But in any way, that's important. So there's a bottleneck here. If your labeling ends up being your bottleneck. Assume an arbitrary table, assume a table with m columns and n rows. Each cell has an information content of q bits. How many different tables are there? And you just have to do the same thing. Information content is just minus log 2, 1 divided by the number of states. And so that is just basically as a consequence, each cell can have 2 to the power of q different states, right? And then there are m of n of it, so it's 2 to, so no, that's not right. So because the columns don't matter, so it's 2 to the power of q times n. Okay, forget m. Oh, how many different tables are there? Okay, then you have to put m in there. Exactly, sorry. So my solution is correct because it's how many different tables are there, not many, yeah, exactly. So there's not, if you ask for the different tables, then of course, with the number of attributes, you could have different tables. So it's a slightly different question. Okay, sorry for the confusion. So yeah, that's correct. Now discuss, why is it problematic to assume the existence of real numbers in a machine learner? The problem is that one real number can store all information of the universe. If you want to have any chance of measuring at all, you have to ditch infinity, okay? Infinity is a mental construct that is super helpful, but it doesn't help you with measurements. That's the big problem, right? So if you want to measure something, you have to actually count. And the moment you have infinity, things become very hard to count, especially if it's a real number, because that's uncountable infinity. You could have countable infinity still, you just say, okay, I have no open end, and then you just count for like natural numbers. But in general, the problem is with infinity is you makes it hard to measure. Or the standard example that I like to give is in calculus, right? The assumption is that between 2 points, there's always another point. Great. If I had that on my bank account, that between 2 cents, there's always another cent, I would be infinitely rich. Awesome. But it also means we couldn't actually do anything. The whole economy wouldn't work. So as weird as it is, infinity is a super useful mathematical trick, but it still is a mathematical trick. And if you want to count anything, then infinity can screw you up. And in this case, it's, yeah, one real number. Obviously, to store one real number would take infinite amount of memory. And so now the reason why we have a Turing machine that has an infinite band is so we can actually deal with real numbers, right? And they didn't want to have that restriction that we have here, where it says, well, the numbers can be really large, but not real. In reality, that restriction that we impose on ourselves, that the maximum number we can store is 2 to the power of n, n being the number of bits, is not so bad, because we know even a 64-bit number is rarely used at all, right? Yeah, so draw the smallest arrow and circle finite state machine for the following functions: 2 Boolean variable nor, the 3 Boolean variable equality, and 2 Boolean variable and 2 Boolean variable or, depending on the input parameter. I would usually do this on a whiteboard. I don't want to do it now because it could take a little bit. Did anybody do this and got the solution? So if nobody has it and get a solution, I can do it and just put it onto my Bamboo pet, which I haven't started right now. I'm sorry. So I'm going to put it in the in the Slack later. I mean, it's just a matter of doing it. But the interesting part of the exercise is not so much doing it; it's that the smallest finite state machine you end up with is 3 state transitions, and you immediately see you can't go smaller. And the 3 Boolean variable equality is absolutely clear. The absolute minimum is 8, and 2 Boolean variable and or 2 Boolean variable or, depending on an input parameter, is also ends up being a 2 or 3, right? So you'll see that. And then there's it's a very simple question again. How many subsets can be created from a subset of n elements, 2 to the power of n? That's sort of freshman stuff, but it's good to remember that. How do you prove that? Well, think about this. You have a set, and now you can include each element, right? So inclusion would be binary yes, or exclusion would be binary no. And of course, now you have n binary yeses and n binary no's, and we don't know what they are, so it's 2 to the power of n again, right? And so this is just important because VC dimension is mostly defined as power sets, and it turns out, yeah, that's just the same thing as doing it as a memory equivalent, right? So explain how creating subsets is the same as binary labeling. I just did that. Assume you have n m-dimensional points in the coordinate system. How many binary labelings can you generate for these points? And that is actually the exact same answer as 1D, is how many car-place labelings can you generate for the points in C is k to the power of n. And again, the point of this exercise is mostly for you to see the language transfer between the traditional VC dimension language and sort of the more engineering way I introduce it, which is like it's just the same thing. You just have to wrap your brain around it, right? So 2 to the power of n subsets of a set come from the fact that you turn on or off the membership in your created subset on each attribute of the original set, right? That's where it comes from. And you can do that with a K labeling too, right? And that becomes that. So obviously you see this homework was just to refresh some of the basics and sort of make you more comfortable with the idea that we can actually express labelings as bits and information content in labelings as bits, okay? Any questions about that? If there are no questions, then let's just dig in. Lecture 6. Okay. Questions can come anytime, and also remember my office hours on Monday at 1 p.m. So last time we said, okay, I have a data set now. Is there any way to kind of get to the maximum memory capacity that I would need for a neural network to implement that function? And here is a point that they said, yeah, there's a simple algorithm. We just set the weights to all 1. And then we get some idea, because it's basically an untrained network. All I train is the biases. And you get what I call the dump network, a network that is sort of learning restricted. It can only do bias training. And then I give you an algorithm, that's the one on the left, on how to train those biases. Because just training the biases, you don't need stochastic gradient descent. You can actually do that analytically, like seen on the left. And that gives you a maximum capacity. So basically the idea is you've got a network trained that just basically is highly restricted, right? All the weights are 1. But then the bigger question was, okay, what would be the expected network, right? And I said, well, guess what? If you're actually able to train all those weights, that's a packing problem, and that's exponential. And since it's exponential, we would hope that, doing all this work results in then logarithmic number of thresholds. And that's a heuristic. That's completely just an idea. There's no proof or anything for it. If you can prove it, send me the proof. But it works. Okay, we use that commercially at this point, and it's really freaking works. It just gives you the expected memory equivalent capacity. But what's also important, I underscore the memory here. I underline that because we're still talking memory. All we have to do is overfit the data, okay? We're overfitting the training data still at this point. There's nothing yet about generalization. Generalization will come today, okay? So we are overfitting the training data. So the dump network is super efficient to build and will overfit the training data mostly with 100% accuracy. And I say mostly because there are sometimes hash collisions. And even if we have a collision, who don't care? We just add another threshold and say, yeah, you know what? The training will wiggle the collision out anyway. So we're good. It's an assumption again, but it works. And then we say, okay, we then take the log of the number of thresholds that we got out there, because we say, well, if you now have to wiggle all the weights, we know, for example, backpropagation is NP complete, that you go and say, well, it's exponential. That means hopefully we can get to log 2n representation. And why is that? Well, because we could also ask ourselves in another way, what is the smallest, if we were just memorizing, remember, we're just memorizing. If we were just memorizing, what is the smallest structure that the neural network could implement? And it turns out that would be just a binary search tree. And of course, we know that binary search trees are log 2 and in depth, right? And so there is actually, you know, in theory, you could wiggle the weights in a way that you get the exact equivalent of a binary search tree. And if you do that, you have the most efficient memorizer you can think of, and that will be logarithm of the number of thresholds. And it turns out there's actually a lot of papers out there that compare neural networks with B trees. B trees are specialized trees that basically have thresholds at the nodes, and they could be like treefold, like is it lower, equal, or higher, and so on. And guess what? B trees, the whole point is that the depth of those trees grows logarithmically with the base of how many thresholds you have in these nodes. And the trick is that they work. They've been used in databases for decades. And yeah, they're memorizing whatever data you put in there in the database. That's what they're used for. And you find that lookup too. The big problem is, what do you do, and what would a B tree do if you gave it data it hasn't seen? Well, but that's not solved here either. We're basically predicting memory capacity still, okay? So, and now empirical results, if we were overfitting AND, XOR, two separated Gaussians, or even ImageNet, how good would that heuristic be that IA gave you, and B, that you can try out yourself on the GitHub, which I actually highly recommend? Well, guess what? I tested it, and I was actually super surprised when I tried this on that ImageNet example, that I was basically off by 13 bits. And that just told me that the expected capacity, taking the log of that maximum dump network, actually worked pretty well. And we tried a bunch of more examples, obviously, after that paper. And again, this is now implemented as part of the commercial product. So it freaking works. Again, if somebody could prove that, that would be really nice. But sometimes you got to just go with heuristics. But all these results are repeatable for you on this GitHub, and I actually encourage you to do so, because you probably will need some of these tools for your project, so you can actually measure out stuff. Now comes finally the point where I will start talking about generalization. We don't want to memorize. We don't want to overfit. We want to be better than that. How are we better than that? And so there comes a little bit of voodoo magic at first, and then we can fight that voodoo magic by thinking about it and restricting ourselves to a certain space that is really useful, and we've talked about it before. So first of all, remember 2, 4, 6, 8, 10, where we say, the next number is 12 based on +2, right? Now, 2, 4, 6, 8, 10 versus 6514. 6514 were the first 4 digits of my phone number. And I said phone numbers can only be memorized. Well, 246-810, there's a rule that can be extracted. So that's better because now I can use the rule on unseen data. And guess what? That is generalization, to be able to do it on unseen data. And now the trick is that 246-810 gives you the rule +2. 6514 gives you nothing, so you can generalize. You don't know what the next number will be. You can't answer that for a random number that I give you. So for unseen data. Now, you could argue, and again, we said before, the point here is we should be using less parameters than predicted by memory capacity, right? Because if you're memorizing 6514 or 2468, then it's the memory required to, memorize 2468 or 6514. But we compare that we found a rule by actually figuring out what the memory equivalent capacity of that rule is. +2 is something like +2. But you could interject, and that's important, you could interject that +0.1, +0.1, +0.1, +0.1, +0.1 until you go to 2 is also a generalizing rule for 246-810. And you would be right. So now I let Mesut speak. Mesut?
Hi, Professor. I actually have this question for a while, but I guess since now you're on this topic again, I think it might be good to ask this question. It might be a good place to ask this question. So I think, what's your opinion on the relations between network generalizing and I guess some of the, unfairness that's a result of overgeneralization by network? Like, how do we know whether or not the network should learn to generalize? I mean, I should generalize. Like, how do we know if network have learned to generalize something that we don't want them to generalize? And is there like a way? I mean, I guess you can use a holdout set to do that. But I guess the question is, network is good at picking up generalization, but maybe some of the issues are caused by the generalization.
So and that's actually, so ultimately you have to test for this one, okay? And there's something interesting there. I think, is Eleanor here? I don't know. I could check if Eleanor is here, because Eleanor and I had a discussion earlier on court cases, right? So what if you use a neural network to model court cases, and basically the question is guilty, not guilty, okay? Just a binary problem. And it turns out we don't want that. What you want is you want the system to actually memorize, to actually overfit. Each court case should actually just look at each case, right? It should be all the factors taken into account such that you actually cannot generalize, right? You shouldn't be able to generalize court cases. And now we were saying, what if you build a model out of court cases and that finds like attributes like race, social status, age, educational status, all of these as the major factors that make it, that you can just use to generalize to 99%, right? That would be a problem, right? So I think my answer to that is what stuff you need to generalize and what stuff you need to memorize is really case specific, like task specific. And another way to put it is, we always talk about rules here. There's always exceptions to the rules. There's always exceptions to every rule. No rule can be complete. In fact, that's Gödel's incompleteness theorem, that there's no set of complete rules to describe a complete system. And it's the same that you already saw my lecture on, which is no universal lossless compression, right? So you cannot compress everything. You know, it's either universal, that means it's like JPEG and you lose information, or it's lossless, and then it means that it's like zip, but that means there are files you cannot compress. And all of these are sort of related to each other. And so with what part of the data you need to generalize and what part of the data you need to memorize is something that really depends on the case. But I would say in general, you need to get to a generalization memorization trade-off which basically you've heard before. It's your bias variance trade-off. Your bias would be how special is your model towards that data, bias towards the data you put in, which is your memorization. And your variance is, okay, how much variance can I take for the input, which is your generalization. So the bias variance trade-off is the same as a memorization generalization trade-off. Does that make sense?
Yeah.
I am here. I just
Okay.
have to wait. I think in answer to the specific, I appreciate the framing of the question of what if it is generalizing based on things you don't want it to generalize on. I think that maybe the answer is that that's okay. The question shouldn't be how do you make it not generalize. The response should be take the fact that it's possible to generalize based on the thing you don't want to generalize on as an indication that maybe your model is not where the answer to the bias problem lies. The bias in the like fairness sense, not the statistical sense.
Yeah. And I think we will introduce measurements later, how to measure bias and stuff that you can use, but ultimately that's just the quality of your modeling, right? So all of this stuff just helps you get better experimental design. And you will have to make a judgment call in the end and say, oops, I generalized over stuff I didn't want to generalize over. And then the question is, how do I fix this, right? Do I need more data with other characteristics? Do I have to take more factors into account, right? And here's another standard example from physics, right? So we have this equation from Newton, E equals mass times gravity times height. And that's the famous example of the apple falling on the head. But we do know that this equation doesn't actually generalize so well. It generalizes pretty much for the range of apple falling on people's head. Because if you drop something from way higher, we know there's something called terminal velocity, where basically the air will stop things, right? And oh yeah, because guess what? The assumption for this dropping was in a vacuum and point-sized mass. We never have point-sized mass, right? We have an apple. That apple is close to a point as it can get, but really the assumption was point-sized and also a vacuum. So now you don't have a vacuum because we never have a vacuum when we drop things. That's just an experiment. Now we have to take other factors into account. And it turns out that Newton's model actually, it doesn't really work if you, let's say, drop something from an airplane into water. It's not clear what the fall actually is until it reaches sort of the ground of the water. It's completely a different equation because it may be a parachute and then it takes for a long time to drop, right? And it may be a parachute, however, that's loaded with, let's say, lead, and now it reaches the water and then it goes down and so on. So it's like the equation doesn't work anymore. You completely, while it's a nice short equation, the assumptions kill you, right? And then you have to think about material densities and all of these more different things. And so for the data that Newton had, we found, or he found the shortest description, the Occam's razor explanation. But then once you slightly modify it, things go completely different. And so that is the reason why all of this here makes sense, but then also it doesn't solve the entire problem. I mean, I'm not solving science in general. It just makes things more engineering. There's more questions. Racist data in equals racist data out. I kind of like the idea. This is actually very timely, okay? And that's the other problem, right? That's where propaganda hits people, right? So the thing here is, if it's racist data in, racist data out, if you give me enough data and let me ignore all the other data, then I may become a racist too, because the point is like, if you only see what they give you to see, right? That's difficult. So the point here is, this gives you a framework that hopefully helps you improve your experimental design, so you can do large-scale experiments with very little number of neurons and with the right goals in mind. But it doesn't solve problems like, should we actually generalize? Should we actually memorize? Which things should I generalize? Which things should I memorize? But I really love the question, Mesut. It's a very important limit of this approach.
Yeah, I think just one more follow up. So I
Yeah,
guess I think definitely if I think that racist data in, racist data out thing is definitely uh, you know, one of uh, the most prominent explanations for, you know, racist machine learning systems.
right.
But I think I guess my question is more about like, is there any way for us in the learning model design process where we can, you know, you can try our best to safeguard against racist or like discriminative
Yeah,
uh,
I'm
like
gonna,
models.
yes, I'm gonna skip along to basically what should be in the next lecture. So the question
Okay.
is, can you measure bias, right? And so the way we actually measure this in the TF meter application, there's actually a little bias meter. The way I suggest to measure bias is the following. You train your model on the data that you have, because that's all you have anyway, right? It would be nice to have different data, but right now it's what you have. And as you train your model on that data, next thing you do is you take the numeric ranges of each column of your data and you generate random numbers. And as you generate random numbers in the same ranges and feed that to your model, you should actually see a 50-50 split as of what the output of your predictions are, right? You should see for a two-class problem that you trained on balanced data, you should see when you go in, that's this an unbiased decision. For unknown stuff, you want an unbiased decision, because bias is sort of unwanted reduction of uncertainty, right? So bias is, well, I have 5 people in a room that are all waiting for an interview, and 2 of them are black, 2 of them are women, and there's 1 white guy. And bias is that the white guy already, just based on his appearance, has a higher chance of being hired than the other 4. And not biased would be, well, I don't know. We have to look at each of the resumes and do the same criteria for everybody. That's unbiased. And so that's basically how you measure this. You basically ask, does the model favor something based even for random people in the room? Is there some favorism, right? And so you generate random numbers in the same range, feed it into the model, and you want to see no favorism. You want to see random data generating random results and not biased towards a class.
I see. But I think my original question is more on the side of when you design an algorithm, like not like after you already trained the algorithm, but like when you're designing it, is there a way to know, okay, what size of, you know, network will be more likely to have this bias versus others? I think, I don't know if that.
Oh, the answer is a straight no. So when you design the algorithm, you can't do anything yet. And the straight no comes from, I think, the exercise you're going to see in this homework.
Okay.
and that is that, remember, the activation function doesn't do anything, right? If I don't know anything about the data, all the activation function does is it splits the data in half, right? And maximally. And whether you give it a shape or not, because I don't know anything about the data, I don't know if the shape does anything, right? And so you have to understand, when you do your algorithm, all you're doing is modeling basically the shape of that split, right? Or maybe of the many splits. And so without knowing the data, your algorithm won't do anything.
I see. I see. All right. Thanks a lot, Professor.
Okay, you're welcome. And these are good questions. And I think I'm really happy that we come up with more and more questions as we go along in the semester. That's actually usually what happens. The first couple lectures are like, what the heck is this? And then it you know, by doing some of the exercise and by doing kind of these discussions, we get further along, and hopefully it starts to make sense. So now let's go from generalization to, sorry, I have to adjust my chat window. Here we go. We go from generalization to, from memorization to generalization. And so what we say is this: in the bias variance trade-off, memorization is no variance, all bias. And that makes it automatically worst case, right? So real world data is not random, right? So that's the interesting part. First of all, wait a minute. We measured everything on completely uniform random data, and actually that doesn't exist. Uniform randomness is a concept like infinity. It's very good to think about, but we never encounter it. There's always some bias. So what it means is, that means actually that, and you will see that if you generate random numbers and you measure the generalization, you actually get slightly higher than 2. Maybe you get to 2, but with enough data, you get to like 2.01 or something. So there's always something that can be generalized, even from uniform randomness. And then or because uniform randomness doesn't exist, so basically even from what you think is uniform randomness. And then the other good news is, and especially that, is that, so by default, by the way, the capacity of a perceptron is not just 1 bit, it's 2 bit per parameter, right? So as you add more attributes, it'll actually get closer to the 2. And the reason why I introduced memory equivalent capacity is because I want to guarantee, right? So now we get to the point and we have to ask ourselves, wait a minute, okay, so Gerald wants to guarantee you can memorize, but then also that's already maybe twice as big as we need, and we're still memorizing, right? So then the question becomes, how small do we need so that we're not memorizing, that we're not overfitting? And there are 2 ways of doing this. First way is, why don't you just start at the capacity, right? So you take out my program and sort of the method, the algorithm that you just saw, and you measure out your data, and it gives you an estimated capacity. And then you build a neural network using the rules that we learned in the lecture before that has the memory equivalent capacity exactly at that accepted capacity. And then you train it. You train it to maybe 98% or something. And if that's not possible, then you increase the parameters, right? So if you can get to a high enough accuracy, you probably should increase the parameters, because maybe you have some regularization term or some weird training stuff that prevents you from reaching full capacity in your neural network. But if you get to high accuracy, what you do then is you say, okay, let's halve the capacity. Let's actually, I'm suggesting halving, but really it's just reduce capacity, take a neuron out, retrain again. Take another neuron out, retrain again. I actually suggest to do binary search. You do half and half and half and half your network until you find, wait a minute, now I can't go up in capacity anymore, go down in capacity anymore without losing significant accuracy. So that's how you get to the bias variance trade-off. You have to actually reduce, 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 reduce. And you do then stop at the minimum capacity for the best held out accuracy, okay? And in the best case scenario, as parameters are reduced, the neural network fails to memorize, right? And it will actually get rid of what's noise, fails to memorize the insignificant bits, and only memorizes sort of the significant bits of the data. Only what really matters is now in your network. And that means you can actually just look at what's really valuable and forget about the details. Sort of for cat and dog, it would be the significant bits of the image are what makes a cat and what makes a dog. And then all the insignificant bits would be all the noise around the image. And so that's where we are. And the curve you should see, and we've seen many, many times, looks like this. At memorization, right, 0 generalization, you get to basically maximum accuracy if you have perfect training or good training at least. And then as you quantize the parameters, as you go further and reduce parameters in your network, you then finally get to less and less and less accuracy, and you get to some generalization, memorization trade-off. And the trade-off should be, as far as I know, at the point that we call n-approx, where we basically, if you quantize enough, we only have noise left. But what I haven't put in here, and what's very important, is basically, and I'm gonna put annotate in here, right? Can I do this? Draw, right? Is basically how the validation set look like, okay? So the validation set, if you completely memorized, right, should be 50-50 for balanced binary classes. Because if you memorized, you know nothing about the validation set and you have no bias. But then as you go up, basically, in reduce accuracy but increase generalization, your validation set should get higher and higher and higher accuracy, because each parameter of the network is now forced to pick up more than one sample. And then you should meet at some point where the accuracy of the validation set and the training set are the same, because you model the same distribution. You find out what makes this distribution its distribution. And then you basically find out that what this is. And after that, by the way, it will go down again. And as it goes down again, you have this problem that obviously you're overgeneralizing, and that may just doesn't give you accuracy, right? So yeah, basically any questions about that? Oops, that curve is now small, but that's how the generalization process should work. You reduce parameters. Let's play this again. If you don't do that, you are at a random point in that curve, okay? It's a random point in that curve, and you may be lucky. You know, the MIT lottery hypothesis paper, yeah, you may get lucky because using your backpropagation algorithm, all the different neurons firing in a random way, and you may just create the equivalent of, instead of +2 rule, of +0.1, +5, -10, you know, basically you get a random chaotic rule. They may actually generalize, okay? And it may work for you, but that's not a systematic approach. What I want is a systematic approach to experimental design, and the only way then is to think about this as actually using too many wheels on my car. Why don't we have 5-wheel or 6-wheel cars for like regular cars? Why? Well, because 4 wheels do it. Why would I use 5? It's a waste of money, energy, and time. It can break easier. And honestly, with all the compute we're doing, it's even bad for the environment. I even put that on the slide because, hey, with all the compute we're doing these days, we are spending we're creating a lot of CO2. There's actually a green AI movement. So it's a waste of memory, energy, and time. But I will give you one more that most people actually don't realize. And that is, first of all, Occam's razor, that less parameters give you a higher chance for explainability. But then there's another one. We can show that the redundant bits in your network, the redundant parameters in your network, are a necessary condition for adversarial examples. They are not a sufficient condition. You can have them in other ways, or they might not have them, but they are a necessary condition. And what that means is that we want to totally, absolutely avoid having them, because if we didn't have redundant parameters, we would get rid of the necessary condition for adversarial examples. How cool is that, right? And we will show that. That's a paper I wrote together with Boli and also Costas Panos, who's here at Berkeley, and Don Song, who is at Berkeley, that one bit matters, explaining adversarial examples as the abuse of redundancy. And let me show that to you, first of all, based on the formal definition of generalization in literature. The formal definition of generalization, which, by the way, I don't completely agree with, but I want to give you what the literature says. So in machine learning, there is basically, the point is, what we have is we have a dog and a cat, right? Or a dog and a dog with noise. So we have an X and an X prime, a dog and a dog with noise. For these two samples, we want some kind of delta such that when we say, well, for some distance measure that we have to find out by using training, that the cat and the cat prime, when they're close enough, within the distance measure, within a delta, that means I will label the cat cat and I will label the cat prime cat too, okay? So we have f of x, that's our machine learner, and then x is some test, x prime is some test data, and x is the training data. And we'll say for all of the training data and all of the test data, we'll find a delta such that x minus x prime, when it's smaller than some delta, that's smaller than some noise, added noise is smaller than some delta, that means that f of x equals f of x prime, and we get the same decision. And that obviously is generalization, right? The lookup table would be such that delta is actually 0. for whatever distance metric you choose, it's only what is exactly in the table. And of course, what we want is we want to have stuff that's it's variance from the table, and that's your variance that you add to the bias that only the table has. Now, the interesting part is that we can create an adversarial example. Just, I need to get rid of, sorry, I need to sort of get rid of that drawing that I made, which is probably just by doing eraser. Here we go, done, okay. Okay, let me go back to the presentation. Okay, so now you can take the definition that I just gave you on generalization and actually just create the counterposition. The counterposition is, sorry, the contradiction, sorry, not the counterposition, the contradiction. The contradiction to the previous is not that, right? And if you figure in the not that and the before, it just means given the model, which is our f function, and a small perturbation delta, we call x prime an adversarial example if there exists an x, an example drawn from the training set, such that f of x doesn't equal f of x prime, while still x minus x prime is smaller than a delta. It's just the contradiction of the generalization rule. That's what an adversarial example is. It's a contradiction of the generalization assumption, okay? It is actually an exception to the rule, okay? And so now you could say, wait a minute, the division community got really hung up on this panda picture and the noise, right? And yeah, fine. But sometimes you want exceptions to the rules. Sometimes something is close to something, but it's not the rule. So a dolphin is not a fish, even though visually, probably it is. But reality is there's an exception to that rule that fish have other things that swim in water and have fins, right? And so sometimes, and Mesu, that's exactly an answer to your question, sometimes these things need to be memorized, right? And then perfect generalization doesn't do it. And so here what I did is I basically said, okay, what if we had XOR plus noise, right? And now in this case, we probably don't want 100% accuracy. It's just noise. So what we want is we want to actually find XOR and ignore the outliers. But sometimes you need to ignore the outliers. Sometimes you need to not ignore the outliers, and it completely depends on what you're doing. Now, speaking of adversarial examples, these are sort of your, this is the explanation for adversarial examples, right? It's your visual explanation for what's going on. Now we get to a little more, let's see, what's the time? Yeah, okay, we have a little time. We get a little more to how would David McKay put it in his information channel, and also what are we actually doing in machine learning? How can we understand that we need convolutional layers? How can we get there? How do we make things happen? Because what will happen is that if you look at real data that comes out of the real universe, like image data, audio data, multimedia data, you will have these outliers all the time. You never have XOR. You always have a lot of noise. So how do we deal with this? And the way I look at this is like, okay, if we look at real world data, sort of measurements out of the universe, then physics should give us the answer to this. And without creating a physics course, because I'm not a physicist, I will give you a little bit of the idea here, which hopefully helps you understand where we're coming from. So this is an information model for machine learning. Basically what we have is, we have our cat-dog classification problem. So we know for some reason the brain can do a distinction between cats and dogs. So we give it 1,000 dog pictures and 1,000 cat pictures. So we have some pattern that distinguishes cats and dogs. And the only problem with that pattern is we don't know what it is. I don't know how to distinguish cats and dogs really, visually. So it's an unknown pattern. And the only way we can observe that unknown pattern, unfortunately, and that's one of the causes it's unknown, is to take a photo, take an image of a cat or a dog. Now we do know that these cat and dog images have that unknown pattern in them, but we don't know what it is, because we always have a background, we always have, you know, illumination. There's always too many factors to just isolate the pattern. We can only measure it with all the noise added, okay? And that would be basically what happens. We have an unknown pattern that goes through a channel, and that creates our observation, right? So the channel would in this case be, you take the digital camera and do it. So the only thing we see is the observation X. Now what we want the machine learner to do is to go and say, no, 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 no. It's nice that you have this observation, but I can look at the million cats and dogs, and now I can decode, I can get rid of your channel noise, and I can get back to Y. I can back to the actual pattern, right? And we do that by giving it a label, right? The interesting thing is now that pattern is in a decoder that we don't know what it does because it's in a big neural network or something. But we can at least reason about it as a black box in a hopefully smarter way than it's usually done. So what a machine learner really does in the case of multimedia, but also in general, is it resets the bits introduced by noise. What you want to do is you want to make all bits 0 of that photograph that don't pertain to your pattern and only keep the ones that do pertain. And as a single processor person, we would say a machine learning denoises an unknown pattern. And as a physicist, you would say machine learning resets the bits introduced by noise. We set those to 0. This seems a little abstract, right? Let's go back to the Boolean example that we had before, okay? So what you have to do when you look at this example is, we now have not XOR again, equality, okay? And what this network does here that you see here, this network will actually calculate the Boolean equality of x1 and x2. That means the output of this network is x1 equals x2. That means it fires in the end if those two inputs are the same, and it doesn't fire in the end if these outputs are not the same. But what I did to this network is I also added an x3. And that's an interesting thing, because what does x3 contribute to the problem? Nothing. We don't need x3 when we look at x1 equals x2, right? Just like we don't need the noise that is added in the picture when we want to see if it's a cat or a dog. And now the question becomes, okay, obviously if I make the two weights, weight 1 and weight 2, 0, then we ignore x3 completely, and then our Boolean network works perfectly. But what if they're not 0? What if they are basically a 1, a 0, or 1, or some trained values? Well, I did that experiment, and you can do so too. And here's what's funny. This network is exhaustive because we only use -1s and 1s, and it's Boolean. So we can actually go through all possible weights for W1 and W2, and this is what I did. So what I did is I called this the allowing edges, okay? Allowing means if W1 is 0, it's not allowing. If W1 is 1, it is allowing, okay? If W2 is 1 and W2, if W2 is 1 and W1 is 1, then they're both allowing edges, okay? And so now we were saying, okay, let's see what happens if I enable the first one or the second one or both. And so obviously you have 0 adversarial example. Oh, what is an adversarial example? An adversarial example is obviously in this case that if you add some x3 of random value, what happens to the comparison that we made between x1 and x2? I mean, is the comparison disturbed in some way, right? Is x1 not equal x2 because stuff, right? Because again, x1 equals x2 has nothing to do with x3. But what we do is we just add that for the academic sort of playground example. And now what we do is we find out, yes, for any other weights than 0, we will always find adversarial examples. That means we can even count them. So if you have one allowing edge, then it's 4. If you have 2, it's only in one case 4. Other than that, it's 6 adversarial examples. So for all the cases that we now have adversarial examples based on the value of x3, which doesn't matter. For the actual function that is super well defined, we get wrong results. And there's something called potential here, which is just basically the weight difference between the weights for x1 and x2 and the weight 1 and weight 2, but that doesn't matter so much. It also has to do with the fact that if you have higher weights, then you get even more adversarial examples. So what it is if you add redundancy to even something as well defined as a Boolean equality, you confuse your network, and you will then have some value be taken into account, x3, that doesn't have to do anything with the Boolean equality of x1 and x2. So redundancies create adversarial examples, and the only way here, pretty much, to not have adversarial examples is to actually not add the noise, okay? To actually make all the noise exactly 0. And of course, that is extremely hard to achieve. You would need the perfect model. And again, that is the information view, where we just basically say we have this unknown pattern, we added noise, and the observation, unfortunately, that the neural network sees, while the task is x1 equals x2, is x1, x2, and x3. And as we train the network, it takes all 3 into account, despite the fact that actually it doesn't matter for the decision if x1 equals x2. And because of that, we have a hard time even to train that. But most importantly, we can show even with exhaustiveness here that, yeah, adding redundancies messes the entire thing up. And unless you can set everything perfectly to 0, you will have adversarial examples. So what you want to do is you want to reduce as much as you can, for example, using convolutional layers, the information that you put in the network, and then make very concise decisions. And now, of course, the question is, yeah, but how does that have to do with parameter reduction? Well, it's the same thing. If we got rid of the parameters W1 and W2 or set them to 0, we would have no adversarial examples. We showed that. And that means that, yes, you want the minimum amount of connections. You want the minimum amount of arrows that are non-zero, which is the same. I mean, arrows that are 0 is the same as not having them. So you want the minimum amount of parameters. And if you did that, if you were able to achieve that completely, you would have 0 adversarial examples. And now we did large-scale tests. We went in and said, okay, how does this behave on MNIST and Cypher10 and on the typical computer vision examples? And this is how it behaves, okay? This is just what comes out of that. And it turns out, yes, if you take a look at your data set and you compress it earlier, get rid of stuff that doesn't matter, that will help. And it turns out in all the data sets here that DeepFool and CW, you may always know better than me. If you measure the complexity, it is always higher complexity. What it means is there's always more information in the adversarial examples than in the non-adversarial examples, giving you further evidence that there's exactly sort of this extra noise added that makes the problem, okay? Turns out adversarial examples always have more noise measured by any sort of complexity measure that we found. One was the entropy here, the other one was something else. I can give you the original paper again. I said it earlier. It's the paper with Bully and Costas and Donson. And yeah, we also find out that if you then increase the capacity to allow for sort of memorization of these adversarial examples, that your error goes down, right? That's basically the point. If you memorize the exception, your error goes down, but now you had to memorize all these exceptions. So it's in there. And However, there's a much smarter way to actually get rid of redundancies in multimedia data compared to just adding a lot of perceptual layers, because the perceptual layers also have to be trained and you have to get rid of them in the right way. And the way to do that is to use JPEG compression or any other information reducer where we know basically the integrity of the image is mostly preserved. And that is actually, now we're getting into the juice of multimedia. The juice of multimedia was also always, how do we reduce information such that the information is mostly preserved? And in the beginning, multimedia started using image processing, using compression, where it's like, okay, I have this Netflix browser, which has like this modem with 9,600 BPS. How do I even display images in my Netflix browser? Well, we in multimedia community invented GIF, the multimedia community invented JPEG, PNG. All of these image formats were used to reduce information, but as much as possible, keep the integrity of the perceptual experience. And the same with MP3 and audio, right? Could we reduce information, keep the integrity, and so on and so forth. And now this is where the multimedia community shines. We go and say, yeah, it's kind of interesting to do deep learning, but really, we've done this in smarter ways before. And then it turns out we did this experiment that it was just the MIPR paper. MIPR? No. Well, the paper that came out in Singapore, we got, in Shenzhen 2 months ago in August. We published that actually JPEG compression gets rid of the need of like 10 layers of a convolutional net, okay? And I will show you where this comes from, why this is the case, and how you can use it, and how you can absolutely use it to speed up your experiments by a factor 100 at least. It's a lot faster. And the first thing here was that. Yeah, so I think I want to stop here and do that next lecture, because that is now we get to finally to the multimedia part of the lecture, and we'll slowly transition into, oh yeah, how does this stuff actually work? And how do we apply this to machine learning, and how do we make good experimental design for it? But I want to give you a joke first, okay? We will be talking a lot about noise, okay? And here's what's interesting. When we talk about noise, people always think, well, but there's structure noise, right? So look at this noise. Look at all these noisy images. If you Google noise, you find a lot of these images. And the trick is this one here has 5 content ID claims since 2015. It's a video. And they say, well, this is an original video, so it's mine. And of course it's original, because nobody can reproduce this without copying it. So there's copyright claims on it, right? There's copyright and patents, and all of this is all based on originality. And it turns out, yeah, noise is highly original. Memorization is required. That means direct copying is required to reproduce this stuff. There's no rule that can be extracted. So it's highly original. But obviously, what we want is we want to argue over this. We want to denoise the unknown pattern. And if we denoise this pattern, the rule would be 0. That would be the empty rule. There's nothing you can do, right? And if you reset all the bits that are introduced by noise, this thing would be white, blank, or blue, or black actually. 0 is black, right? It would be black. And the same here. Now, maybe not if you find extra information in there. So white noise is the noise that comes from uniform random distribution, which also never exists. But then there's also pink noise, which is a Gaussian distribution. And there could be brown noise and various noises which come from other distributions. And then obviously you have some bias in the noise, which you could extract. And of course, Gaussian noise, we know the bias. It's just the Gaussian formula, right? That's the bias for that noise. So the trick here is that we need to start with the notion that noise means memorization, right? And as we get rid of memorization, of the part of memorization, we allow for more variance to get to the same result. And as we do so, we get rid of adversarial examples, and we also get to better models. And something like this, the answer is we cannot model it. The best model for this is the black screen, and then you add random noise to it, right? And so if you really want to reproduce this data set sort of in the information sense, you have to memorize each pixel. And the only way to do it is to copy it. And of course, the Shannon entropy of such an image is very high as well. And so you cannot denoise the pattern because there is no pattern. It's the empty pattern. Yeah, before we go into the next part, which is doing a little bit of physics to understand how we can use this and how we basically separate noise from non-noise. So we get an idea of how many convolutional layers or how much JPEG compression up front we need. We will measure that in the next lecture and sort of really get into the gist of how multimedia data works and how it connects to everything you've seen so far. For now, I want to say thank you and questions. Okay, I'm sure there will be questions. Oh yeah, Mesut.
Yeah. So so if noise, so I guess there's different types of. Okay, so I think the noise that you mentioned in your lecture are more of like random noise. For example, they probably just do like 0 to 1. I guess maybe they just populate the entire image like that. But what if there are but what if there are patterns in a noise? For example, if you know that the noise come from like a particular type of source, for example, you can, I don't know if that makes sense, but you look at the space of noise and you realize that, okay, the noise I'm getting is mainly coming from this very small set of all possible noise that could be generated. But so does that, does capturing that distribution, first of all, is it possible to capture that distribution? Second of all, what are the way, like if it is possible, how do you do it? And if it's not possible, why?
Good. I love this question because before deep learning, that's what we were doing. We were trying to capture the distribution of the noise and then use that as a denoising so that we end up with a distribution of the non-noise. That is what signal processing has been done for decades. And now just with deep learning, the idea was, oh, this is too much work, let's get rid of that. And it turns out there's no free lunch. This deep learning can do some of it, but now we don't understand it anymore. And we use so much computational power for special cases, right? So the trick here is that absolutely, there were things like the Wiener filter, which I will introduce in a couple of lectures, which were trying to model the signal to noise ratio and then made speech better. The Wiener filter works, it's a miracle almost how well it works. It's so simple and it works. And there's other various ways of obviously modeling the noise and subtracting noise from the signal. And yes, we are absolutely able to model that. And more importantly, JPEG is modeling the noise. It's basically saying everything I perceive needs to be stored, and everything I don't perceive, I call that noise, and I get rid of it. And that's what JPEG does, that's what MP3 does, and that was what basically the trick of the multimedia community, and also of the signal processing of the audio community and of the speech communities and of the computer vision communities were for decades. And now I'm not saying we should go back to that. Well, actually, maybe I'm saying that a little bit, because what I'm saying is, if you want to understand your signal and if you want to have a robust thing, then you need to take into account what these people did when you do your deep learning algorithm. And that's sort of the trick. The trick is to realize, is my network good or bad at what it's doing? And if it's bad, then probably I should use a different technique, right? That's exactly, I think that's exactly answering your question, is it?
Yeah, I think it's definitely it actually helps. But I think my okay, I don't know if yeah, I probably can't get into this question without mentioning my I guess my domain, but I guess so I mainly work in the domain of human robot interactions.
Mm-hmm.
So the noise that we constantly deal with is like humans I guess suboptimalities, which I'm
Right.
yeah. So basically I mean, there being like the I guess the more old like pre neural network era model of noise is the Boltzmann's model, which is basically you kind of like Boltzmann irrationality, which I think works reasonably well. But I think I'm not really sure if there's a way to design neural network to basically model that kind of thing. I mean, I think people nowadays they do some neural network and they do some like Boltzmann stuff on the side. But like, do you think there'll be a way for neural network to capture, for
No.
example?
So what you want to do is you don't want to model the noise because you can't model the noise. The noise has no rule to it. That's why it's noise. You want to model the rule, and by knowing the rule, you can ignore the noise.
Wait, what? But but I think I thought the point is that there's really
If you
like
know this, no, if you know the source of the noise, then it's different, right? If you know the source of the noise, then you can have a model for the source. But if you don't know the source of noise, it's something like human noise, for example, then you want to model the rule. Let me give you an example. 2, 4, 6, 8, 10. Again, the standard example. You have heard it every lecture. But what if I said 1.9, 4.1, 5.8, 7.6. Now the rule is still +2, but we can't really say what the noise is. We just know, well, it's +2 except plus minus some epsilon. That's how I would suggest to do it if you don't know the source of the noise.
yeah. So I think using that example, I think a good way to explain this is probably like for some people it will be like 0, 1.8, 2.2. I mean, like relatively small perturbations, but for other people it will be 0, 1.5, 3.7,
Yeah,
right? Like it will be like people will have various degree of noise, but
and that would so
there's
you
correlations between like the different observation you get for a single person. But I guess the pattern is not really distributed uniformly across all the people. I don't know if that.
so if you have data that has more noise than signal, we'll call that chaotic. You can't model it. That's what it is. So basically, if you have more noise than data, that's it. Your data basically vanishes in the noise. And then you probably have to do something like model the noise source and reduce the signal to noise ratio bit by bit by bit by bit. But in general, if you have too much noise, then you can't model it. It's just not learnable. It's like all of these pictures here.
Yeah, but what if it's sequential and inside, so there are relations between the distributions inside a single trajectory, but so basically like if I look at this person, then this person is I don't know how to explain it, is less, for example, good at planning ahead than another person. So this person is more likely to make some heavier mistakes, whereas another person who's probably a little bit more aware, their action will be less noisy. So I don't know if that makes sense.
Yeah, so again, if you can create a model, then you're good. But I'm just saying, you asking me, but what if it's too noisy? The answer is then you cannot create a model, right? I mean, what I would suggest, and we can take this offline and maybe take a closer look at your problem in the office hours, is to actually think about what you can model. So if you see patterns, what you're saying to me is you see some patterns. Well, patterns are modelable, but patterns are not noise, right? That's the whole trick. So yeah, maybe let's take that into office hours and
Okay, sounds
go
good.
deeper in this. Okay, cool. Yeah, but thank you everybody for questions, and also the lecture again will become more practical and will become more questions and answering soon. So also please use the office hours, please use everything to just sort of at your disposal. I know it's COVID and everything is weird right now, but again, also thank you everybody for showing up, because making it interactive is very important, and I want to answer questions like Masood's and Eleanor's. Thank you very much. I'm going to stop the recording. Oh, I should have done that earlier, but okay, stop recording.